AP Cacus BC, Unit 8, Day 6, Office Hours. These are the answers to the multiple choice questions. At the top, pause the video if you need to check them. Okay, assuming that you have checked them, let's do these. So, first problem, they're giving you a series, an infinite series, and it looks like they're wanting to know what it equals, so the sum. So I think really our only shot is if this is a geometric series. So it might be worth it to just try and rewrite it into something a little more like a geometric series. Now, if you plug in k equals 0, you get 3/10. So we could bring that out, and then it's just 1 to the 10th k. So this is the same thing, right? And I think that makes it a little more obvious that it is a geometric series, that the a value is 3/10, that the r value is 1/10. Diverges could be an option on these, so if that was, you would want to make sure that it met the condition for convergence. So it does converge. So the sum is a over 1 minus r, so 3/10 over 1 minus 1/10. So 3/10 over 9/10, which is 3/9, which is 1/3. And there it is, 1/3. Okay, number 2, the formula for the nth term of the series. So we're trying to find the formula for the nth term. I find it easier to write the n values below it and see if I can see a pattern, which I think I'm starting to see already. It looks like 1 over 2 times n plus 1. All right, 2 times 1 is 2, plus 1 is 3. 2 times 2 is 4, plus 1 is 5. But you also have this negative thing, so you need a -1 to the n power. Now that's if we start at n equals 0. If we start at n equals 1, it would be different. But see, I don't know if I see this one on here. I don't see this one on here. So the other thing to consider is if we start at n equals 1. Now if you start at n equals 1, then the pattern is 2 times n minus 1. 2 times 1 is 2, minus 1 is 1. 2 times 2 is 4, minus 1 is 3. So it would be 1 over 2n minus 1, and then it'd be -1 to the n minus 1 or plus 1. So do we see something like that? 2n minus 1. So I think it's going to be this one right here. It could be plus or minus 1. You just got to make sure it's even on the first one. So there you go. I mean, this would be what it would be if we started at 0. And this is what it would be if we started at 1. So, I mean, another way to check, I guess, is just plug. Yeah, I don't know. That's our best bet. Okay, number 3, use the formula for the sum of geometric finite geometric series. So this was, we talked about this, I think, on one of the assignments. I think we could figure it out without having the formula. But so this is a power series, and I would say the a value is 1 and the r value is x. So for the infinite series, you would say, okay, well, the sum is a over 1 minus r is 1 over 1 minus x. So that would be the infinite series, right? Then if we're starting at the next term would be the nth term, right? That's nth minus 1. So if we did that one, we say, well, a equals x to the n would be the first term, and r equals x still. So the sum would be a over 1 minus r, would be x to the n over 1 minus x. And so the sum of the finite series, the infinite, minus this infinite one would leave you with that. So If we do that, they have the same denominator, so that's convenient. And do we see something that looks like this? 1 minus x to the n of 1 minus x. There it is. Didn't even need a formula. There is a formula of it. We've used it so little that there's no way you remembered it. So that works. Okay. Next page. Number 4. Number 4 says the first 3 terms of the Maclaurin series for this are these terms. So I don't know if you guys remember how we got the Maclaurin series for this. It was 1 over 1 plus x, and then we integrated it, right? And 1 over x, the first term was 1, and the r value is negative x. I'm just throwing this out here because I think this is good if you can just crank this out real quick. So if you integrated both sides, and we know x is between negative 1 and 1, that's why we don't need the absolute value. So it would be x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. So, we're trying to find that. We're trying to find the first 3 terms. So you could do it like that. I think that's the fastest way. X minus x squared over 2 plus x cubed over 3. The other way to do it is much longer. The other way to do it is to say, okay, well, that's the original function. So you can build it and you say, okay, that's like the 0th derivative. The first derivative is 1 over 1 plus x. The second derivative, you have to go, it's like possibly up to the 3rd derivative. This is the same thing as 1 plus x to the negative 1. I mean, this is generally probably not what you want to do, right? It's not too bad. It's not bad. We should get the same thing. So then, because it's a Maclaurin series, it's centered at x equals 0. And so natural log of 1 is 0. We get 1. We get negative 1. And we get 2. So then it's a Taylor series, Taylor polynomial. So 0 times x minus the center to the 0th power of a 0 factorial plus 1, x minus the center to the first power of 1 factorial plus negative 1, x minus the center to the second power over 2 factorial plus 2, x minus 0 to the 3rd power over 3 factorial. Now this simplifies way down. That's 0. This is x. This is minus 1/2 x squared. This is plus 2 6 1/3 x cubed. And then it keeps going. Same answer. That was a lot more work though. It's good to know where these came from. And I don't want to purely memorize it. I don't think that's going to work out. So this is what I have to do if I can't remember how to get it. But this is my trick for remember how to get it. Which of the following is the approximation for cosine of 0.1 using the first 3 non-zero terms of the Maclaurin series? So the Maclaurin series, it's a power series. So say we'll cosine, what's the cosine series? I have these memorized. It's the even terms, right, of the e to the x series. So the first term, 1, is considered an even term, like 0th power, 0th derivative, and then minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and keeps going. And it's alternating too. You gotta remember that sine and cosine are both alternating. So we're plugging 0.1 into this to estimate 0.1. And it says using the first 3 non-zero terms. So 2 factorial is 2. 4 factorial is 6 is 24. So do we see something that looks like, now 0.1 squared is 0.01, right? 0.1 to the fourth is 0. It's essentially, it's 1 over 10 to the fourth, so it's going to be 1 over 100,000, 10,000, right? So tenths, hundreds, thousands, 10,000ths. That's what this is. So we're looking for 1 minus 0.1 over 2. So that looks good. Plus 0.0001 over 24. So these are missing the factorials. So I think this is it right there. There you go. Number 6, there is no Taylor polynomial for this function, Sarah, x equals 0, because, so Taylor polynomial centered at x equals 0 requires that you evaluate all these values at 0. So this is x to the 1/3, right? And if you start taking derivatives, you get 1/3 x to the negative 2/3, and then you get negative 2/9 x to the negative 5/3. And the problem here is that when you plug 0 into these, you get undefined, right? You get division by 0. You get a value on the first one. But all these others, you can get undefined for all of them. So we can't do that. So I would say, why? Because f is not continuous. It is continuous. It's not differentiable. I think that's what I want to go with, because we need the derivatives, right? So it's not differentiable. That's a problem. Okay, number 7, use the 5th degree. Okay, that's different than 5 terms. 5th degree is the highest power. Taylor polynomial find sine x. For sine x, to find the 5th degree Taylor polynomial sine 2x. So essentially, this is like those Maclaurin series that we've memorized, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, right? That's that one. And so sine of 1/2 x, we could just plug 1/2 x in every time we see one of these x's. Otherwise, you could do it the long way. Now, which of these seems to match up with that? I mean, this is x over 2 minus, a lot of these have, like, that's x cubed over 2 cubed, right? 3 factorial. So x to the 5th over 2 to the 5th, 5 factorial. So this is what we're looking for. And there's probably some that are really close to it. This one doesn't have the factorial, so that one's out, right? This one's plus, minus, but this one doesn't have the cubed in the 5th, so that one's out. This one's good, except it's not alternating, so that one's out. This one, that one looks good. So they have ones on there that all look kind of close. This one, again, isn't alternating, so that one's out. So there you go. Number 7. Okay, number 8, the first 3 terms of this Maclaurin series. Well, I would just say, okay, well, what's e to the x? We memorize that. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so forth, right? E to the negative x would be the same things, but with a negative x plugged in. And the negative gets squared, so it becomes positive. The negative gets cubed, so it becomes negative. And you get that series. And so then we're going to add these up, and half of the terms are going to cancel each other out. So we're going to get 2 plus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial plus dot, dot, dot. And then we're going to divide everything by 2. So that's going to cancel all the 2's out. So we're back to 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial. And on and on and on. So that matches answer B. The other way to do it is to take lots of derivatives and build them up. It's a lot of work. A lot of work. I wouldn't do it that way. Okay. The function f is given by the Maclaurin series. So here's a Maclaurin series on the interval convergence. What is f of 1/2? So I guess what we're trying to do is maybe look at all these answers. They have natural logs and e's and stuff. So I think we're trying to recognize what special function this is. So it starts with yeah, I don't know. I guess we're just trying to recognize it. The a value is x. The r value. You know what this looks like? You see how it's x squared over 2, and they're not factorial. So this looks like it came from integrating something, right? So what is that, the integral? That's the integral of 1 minus x plus x squared minus x cubed, right? Do you see that? So I think this is from that integral. And this is the integral. This is the a value equals 1 and r equals negative x. So that the sum of that is 1 over 1 1 over plus x, because it's 1 minus. So that's why we're integrating here. And the integral of that's natural log of 1 plus x. So it looks like that's what this represents. This is natural log 1 plus x. So if you're to plug 1/2 in here, you should get natural log of 3/2. That one's kind of tough. Kind of trying to work backwards. That was kind of tough. Okay, number 10, the fourth degree Taylor polynomial for either the 2x centered at x equals 0 is what? Now, I want to do the shortcut here. I want to say, well, I know e to the x is this. I've memorized this pattern. It's a pretty simple pattern, right? So then if we put e to the 2x, that means we're just going to replace every x with the 2x. But whatever's being done to it has to be taken into account and applied to the 2x. So we can crank these out. I mean, the alternative is taking all the derivatives of e to the 2x, which isn't hard, it's just tedious. So centered about 0, that's what this one is. That's a Maclaurin series. So I'm looking for something that looks like this. Now, I don't think I necessarily need to simplify this for me to match it up, but it is going to be 4x squared plus 8x cubed plus 16x to the fourth. I mean, you can do that if it helps. I mean, that's the way all these answers are written. So anything that doesn't have a 1 in front, that one's out. It's got to be all plus. So the ones with minuses are out. So it's between these two. This one doesn't. The x's are supposed to. The 2's are supposed to get the power. So this person didn't. So that one's out. Let's see. Okay. Next one. Okay, number 11. Find the fourth degree Taylor polynomial centered at x equals 0 for this function. Well, we can actually build a function for this. We can say, okay, well, cosine x it's the even terms 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and on and on and on. That's cosine. So 1 minus cosine is just going to be 1 minus this. Okay, so we got to distribute the subtraction, and so these guys are going to cancel each other out, and it's going to be positive x squared over 2 factorial minus x to the fourth So we still have the alternating pattern, but it is at a new spot now. So I think we're looking for this. X squared, we're saying fourth degree, so that just means this. Highest power is the fourth power, so that one's out. But x squared over 2 factorial minus x to the fourth over 4 factorial, so it's D. All right, graphing calculators allowed on these problems, so I don't know, let's see how they help us. Use the fourth degree Taylor polynomial for cosine x entered at x equals 0 to approximate cosine of pi over 6. So what is the fourth degree Taylor polynomial for cosine x? Let's write it down. Cosine x equals 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6th over 6 factorial. Okay, so this is the fourth degree Taylor polynomial, and we're going to use it to estimate cosine of pi over 6. So that means we're going to plug pi over 6 in to these. So it's this value. This is where I'm going to use my calculator. So I'm going to do 1 minus pi divided by 6 squared divided by 2 plus pi divided by 6 to the fourth power divided by 24, 0.86605. 0.866. So there it is. Now the actual value of cosine of pi over 6 is actually very close. It's pretty impressive though, right? I mean, it's close. It's off on the 5th decimal point. Okay, number 13, if px, which is usually how we indicate Taylor polynomials, third degree Taylor polynomial for this function, so x equals 1, then what would p of 1.2 be? So let's find the third degree Taylor polynomial. Now, center x equals 1, so we're not going to use, I don't think we're going to use those memorized patterns. Those are from the Lorentz series centered at 0, so I think we need to go ahead and find the derivatives. 1 over x, which is x to negative 1, and then the second derivative is going to be negative 1 over x squared, and the third derivative is going to be positive 2 over x cubed, and then we plug 1 into them, so natural log of 1 is 0. That's going to be 1. That's going to be negative 1, and that's going to be 2. And then we build it. Taylor polynomial, third order, 0 times x minus 1 to the 0 power over 0 factorial. Those are both 1, but there's a 0 in front, plus 1, x minus 1 to the first power over 1 factorial, minus 1, x minus 1 second power over 2 factorial, plus 2, x minus 1 to the third power over 3 factorial. It keeps going, but we want a third degree Taylor polynomial. So we're going to plug 1.2 into it. And that's going to be 0.2 minus 0.2 squared over 2 plus 2 times 0.2 cubed over 6. So I'm going to put that in my calculator and see what I get. 0.2 minus 0.2 squared divided by 2 plus, you could make that 1/3, just make it easier. 0.2 to the third power divided by 3, 0.18266, which this is the closest to it. I'm assuming they're rounding. If it's rounding or truncating, they wouldn't give you both options. Now, let's see. That is supposed to be an estimate for a natural log of 1.2. So what is natural log of 1.2? Pretty close. Pretty close. Off on the 4th decimal. But that's how your calculator does it. I mean, we just took a few terms. The infinite terms will get it exact, but that's just unnecessary. So that's it. That was some good practice there. What we've learned so far. become really good at this stuff.